Good morning, everyone. I'm Rubaiya Rumman. I am a PhD student of civil engineering at the University of British Columbia, Canada. And today I'm going to present an interesting topic titled "A Study on the Mechanical and Durability Properties of Rubberized Concrete." And my co-authors are Salama Mehriya, Dr. Mohammad Tiznawaik, and Dr. M. Shahriar. So the contents of my presentation are the background studies, and then the experimental program, then the results and discussions and conclusions. So concrete is the second most consumed material after water, which makes it the most consumed man-made material on earth. And the reason behind its huge popularity all over the world is the reasons are like the global availability of its constituents and its low cost and flexibility in forming shapes. However, this ubiquitous material is a huge emitter of carbon dioxide, as my previous colleague also mentioned in his presentation, that 1,000 kg of cement production emits about 900 kg of carbon dioxide, which is a lot. And if you look at the pie chart, you can see that concrete is solely responsible for 8% of the annual global emission per year, actually. So this needs to be reduced. I mean, the carbon footprint of concrete needs to be reduced. And one approach is using waste and recycled materials, replacing the virgin constituents of concrete. And some materials, waste materials and recycled materials that are used in concrete are the construction and demolition waste, crown rubber, wood ash, plastic waste, e-waste, and there are other different materials too. But the focus of my study today is the crown rubber particles. We use crown rubber to replace sand at different levels, and we investigated the mechanical and durability properties. So rubber usually comes from the waste tire, and every year 1 billion tires are discarded, and about half of them are properly recycled. They are made into crown rubber and they are used in construction and like that, but the other half goes to the landfill. So it's a huge concern since rubber is non-biodegradable, so it causes a serious hazard to the environment. So these pictures show the process of making the crown rubber from the discarded tire. The tire is first shredded and made into tire chips, and then they are grinded and made into crown rubber. So we can use crown rubber treated or untreated in concrete as a replacement of sand or coarse aggregate. To focus on our experimental program, the materials we used for making our concrete samples were cement, that was general use cement, and as fine aggregate we used sand, and we replaced sand with crown rubber at various percentages, and for coarse aggregate we used gravel. So these are some of the properties of the materials that we used. The first figure shows the gradation of the sand, and the next figure shows the gradation of crown rubber. So you can see that both the sand and the crown rubber followed the CSA upper and lower boundaries, and also we used well-graded crown rubber. We mixed 3 sizes of crown rubber and then made a well-graded version of crown rubber, and then we used that to replace sand. And this table shows various properties of the aggregates, and this one shows the composition of the cement that we used. These are the microscopic images of the crown rubber particles at various magnifications using the scanning electron microscopy. So you can see that the crown rubber particles are angular and fragmented, and their shape tells you that it can entrap a huge amount of air in the matrix, which accounts for like the low weak bond between the matrix and the crown rubber particle, and also as you will see in the results and discussion part that it makes the fresh mix a little bit harsh since there is a lot of air entering inside. So these were the mix design that we used. We used the one control mix, and then we used 3 levels of replacement: 10%, 30%, and 50%. And we replaced sand in a volumetric manner. And so these are the mix design, the 4 mix designs we were used. The tests we did were, for the fresh property we did slump, and for mechanical properties we investigated the compressive strength, and we looked into the failure pattern. And we did 2 durability tests, one freeze-thaw durability and one rapid chloride permeability test. So these are the images of our experimental program. The first one shows the slump, this one is the compressive strength, and freeze-thaw durability and rapid chloride permeability test. So if I go to the results part, these figures show the slump variation of the mixes, the fresh mixes, with the addition of crown rubber particles. So you can see that the highest slump we got was for the control mix, and gradually with the increase of crown rubber, the slump value decreased, as we saw in the microscopic images that because of the fragmented shape of the rubber, there are a lot of air entrapped in the matrix, so which accounts for the lowering of slump, which makes the concrete less workable too. So up to 10% level, the reduction in slump is not that significant, but after that, like at 30% and 50%, sorry, the slump is hugely reduced. So and this figure shows the compressive strength results of the mixes. So the control mix definitely showed the highest compressive strength, and the 3 columns are signified the compressive strength at various curing ages, that's 7 day, 28 day, and 56 days. So the strength gradually increased over time, but with the increase of crown rubber in the concrete resulted in the decrease in compressive strength. And here we also can see that up to 10% level, the result is quite comparable with the concrete control concrete. And you can see that at 28 days, the strength is more than 35 MPa. So it's quite comparable with the control one. And but still, with the addition of crown rubber, because of the weak bond between the crown rubber and the matrix, we see that the decrease in compressive strength. So but there is an interesting find if you look at the failure pattern of the concrete, that we found that for the control concrete, the break was like more brittle, and with gradual inclusion of crown rubber, the failure was more ductile. So by the time we used like 50% replacement, we got quite a lot ductile failure compared to the control one. That's because of like crown rubber's huge energy absorption capacity and its deformability. So this was one interesting finding. And these are the results of the freeze-thaw durability. We put the samples in the freeze-thaw chamber for 300 cycles, and all of the samples like resisted the 300 cycles. They did not break during the test. And the first figure shows the relative dynamic modulus of the modulus of elasticity of the samples, and the x-axis shows the number of freeze-thaw cycles. So the decreasing trend is because of, when you put them in freeze-thaw cycle, then the concrete deteriorates and cracks form. So that's the decreasing trend. But if you see that the control one showed showed the lowest relative dynamic modulus of elasticity, and it gradually improved with the addition of crown rubber. So and if you look at the weight change figure 2, you can see that like weight change was the highest for control and the lowest for crown rubber. So both of these figures show that crown rubber particle worked better in terms of durability, freeze solubility. Sorry. That's also because of its deformability, rubber's deformability, and since its deformability resisted the microcracks forming in the prisms. And this is the results of the rapid chloride permeability test. If you are familiar with the test, that we put a slice of the concrete and we put like a potential and we let current pass between them. So the more the charge passed, the more permeable the concrete is. So which means it's an indirect measurement of durability or permeability. So, and ASTMC 1202 also gives us this classification table where you can see that the moderate permeable range is 2000 to 4000. So our control mix was in the moderate permeable range, and while all the rubberized concrete was in the low permeable range. So the chloride permeability also improved with crown rubber addition. So if we go into conclusions, that crown rubber reduces slump, crown rubber reduces strength, and however we can see that the failure pattern, that it gets more ductile with the addition of crown rubber, and also the durability was better in terms of when we use crown rubber. So crown rubber significantly improved the durability of concrete. And considering the composition, durability, and failure pattern, and for all the four mixes, we could suggest that a 10% replacement of the fine aggregate with crown rubber can be an optimum percentage for rubberized concrete, considering like the environmental impacts and all other things. And here I forgot to mention that our target strength was 35 LPa. So we can use that for our sidewalks and structures like that. So it can be a good addition and also like a good way to reduce carbon footprint of concrete. So I want to thank our lab and from UBC and NSARC for their financial support, references, and thank you. If you have any questions, please feel free to ask.
Thank you.
So, you mentioned that the use of crown rubber resulted in higher energy absorption. Was there any study to?
No, it's from literature actually. We did not study the energy absorption,
Yeah.
but in the literature, I quoted that from the literature that it has high energy absorption capacity. Yeah, but if you can see at the failure pattern, it's an indirect. I mean.
Yeah, if we have the
Yeah.
stress curve,
Yeah.
so we can.
Yeah, yeah. We actually did that, but it's not in the scope of this conference paper actually, so I did not show that.
Because the replacement of aggregate was based on volume?
Volume, yeah. Yeah.
And also, did you do any treatments on?
No, it was not treated. We had another study going on. We have another study going on where we used sodium hydroxide treatment. But since the target strength was low for this study, I mean, like we only non-structural purpose we use this concrete, so we did not use any treated crown rubber. Yeah. But we graded them in a mid-grade manner.
You considered using this rubberized concrete with reinforcement? The bond strength between the reinforcement and...
Yeah, that can be a recommendation. Like with since we see that obviously the bond deteriorates. I mean, with the addition of crown rubber, as there are a lot of air entrapped there. So since we got 10% quite comparable result, we can use that with reinforcement and see how it behaves. We have, there are other projects are going on where they're considering like joints and stuff with crown rubber, but it's an ongoing project.
Okay, well, thank you for your presentation, and let's move on to the next